So in this video we're going to look at how we can use the equation I equals nVQA or nAqv to explain or investigate what's happening inside wires when they're connected together or inside different types of component, or if temperatures change, things like that. Exam questions really. So I'm going to talk you through one example and then I'm going to give you some to do yourselves and I'll go through them afterwards. So a typical question might be something like this. We've got two wires, A and B, connected in series. A has clearly got a larger diameter than B and therefore a larger cross-sectional area. And it tells us that there's one amp flowing through them. So what would we have to do to sort of answer this question? Well, first of all, we need what we know already about series circuits. If A and B are connected in series, the current is going to be the same in both of these wires. So what we have to do, the way we approach this, is we ask ourselves what's the same in the two wires and what's different between the two wires. So if I was just sort of sketching it down on a bit of paper, I might start with this equation and I'd say to myself, okay, well, because they're connected in series, the current is the same in both of those wires. Now, N is the number of charge carriers per unit volume, and this is where some people go wrong. A would have more charge carriers in it, but they're made of the same metal. I mean, I haven't said it in here, but if it was an exam question, they definitely would say that. So the number of charge carriers per unit volume will be the same between A and B. So the N is the same. Right. What about Q, the charge on each charge carrier? Well, that's going to be the same as well, isn't it? Because they're just electrons. So that's the same. So what does that leave us with? Well, we know that the area is different. We know the current is the same. So what we can say is, well, the area as it goes from A to B has gone down. If the area has gone down, to keep the current the same, the drift velocity must go up. Now, how would I write that down? Well, I've got that hidden under here, and you might want to make note of this. So I start with the equation. I note that the current's the same in both wires as they're in series. The N is the same because they're the same type of metal, same number of charge carriers per unit volume. The charge on each of those charge carriers is the same. And then I'd say something along the lines of the area is less in B, so the drift velocity must increase to keep the current the same. Approaching it this way lets you answer all sorts of questions related to this equation. So I'm going to go on to the next slide with a slightly different example. Right, this time you can do this yourselves, but it says compare the drift velocities in these two wires. Now this time they're the same diameter, current's the same, it's in series again, but we've got copper and lithium. Now no one's going to expect you to know this. They would have to give you the information, but it turns out that copper has 8.5 times 10 to the 28 electrons per meter cubed, whereas lithium has a lot less. So using that bit of information, try and recreate what we did in the last slide. Okay, I trust that you've written that down yourselves and come up with your own answer. Here's how I would approach it. I would state that the current is the same in both wires. The area is the same in both wires. The charge is the same in both wires. But when it goes from copper to lithium, what we have here is that the number of charge carriers per unit volume goes down. So in order to keep the current the same, the drift velocity increases. And hopefully you've written that up neatly. Okay, let's try another one. Right, why does the current decrease when the wire is heated? This requires some of your year 11 knowledge, and you need to know what happens to the resistance of the wire and use a bit of intuition to see what that would affect up here. So over to you for a second. Welcome back. All right, so this time, I haven't said anything about the current in the wire. We're saying that it's going to decrease when the wire is heated. So let's look at why that might be. Well, some of you might go down an angle of saying, well, if you're heating things, they increase in volume, they expand, so the area, but it'll be negligible. So we're going to say that the area is going to stay the same. Q stays the same. Number of charge carriers stays the same. But remember, the drift velocity comes from the electrons, which are moving individually very fast, colliding with the ions in the wire. Now, if the wire's heated, the ions are going to be vibrating more, so that's going to increase the number of collisions, and that would reduce the drift velocity. So the drift velocity would go down, and therefore the current would go down. This would be completely opposite if you were talking about a thermistor. Because in a thermistor, when you heat it up, it releases more free electrons. So in a thermistor, the N would increase. The V would also decrease, but the N would increase a lot more than the V decreases, so overall the current would go up in a thermistor. I mean, all of this is assuming the potential difference across this stays the same. Okay, and then a final one, which I'm sure you can do yourselves. It says, why does the current decrease when the wire is stretched? And basically we've got the same amount of material, but stretched thinner. So what's going to change? The area is going to change. So could you now write out, using the same ideas that we've had a minute ago, why the current would decrease, sorry. Okay. Finally, I'm going to ask you to go and do some past paper questions on this now. But I've got one where they might ask you a numerical problem. They might ask you to find, say, a ratio of the drift velocities in each wire. And I just want to show you the sort of thing you'd have to think about for this sort of problem. So I've done this twice. I've done it, and I think on the next slide it's a slightly shorter, simpler way. On this slide I've broken down every little step. So we start with the same problem that we had earlier on. We've got A and B. A has got twice the diameter of B. The current in them is the same. That's important. So I've started by jotting down the equation, I equals nAqv. Unfortunately, the question's been irritating and talked about diameter instead of area. But we know an equation for area, that's pi r squared or pi d over 2 squared. So I've replaced that in these equations. So I'm going to scroll this up and let's see what we've got. So what I've done, I've said the current, which is the same in both wires, so I can equate both of these equations, is equal to the number of charge carriers, pi times d over 2 all squared, times q, times the drift velocity in A. Then in the second wire, the n is the same, but this time we've got half the diameter. So I've missed a slight step out here, but I'm sure you can see this. I've halved this diameter, so d over 2 becomes d over 4, all squared, times q, times the drift velocity in v. Now, when you look at that, most of these things are common or constant between these two equations. The n is the same in both of them, the pi is the same in both of them, so they cancel. The q is the same, so that cancels. So it becomes a lot simpler and nicer to look at. We get d over 2 all squared times VA equals d over 4 all squared times VB. And now, you're a lot younger than I am and you do a lot more maths than I do, so you probably find the next step much simpler than I did, but I'll step through it bit by bit. I expanded this out and I got d squared over 4 times VA equals d squared over 16 times VB. Keep going, the d squares are on both sides, so they've cancelled. So I get a quarter of VA equals a 16th of VB. I'm sure you know what we'll do next. I've got 16 times VA equals 4 times VB, so I've just multiplied the 4 and got a 16 up to here. And we get that 4VA equals VB. So basically the drift velocity in VB is 4 times greater than VA. And writing it as a fraction, we get VA over VB equals a quarter. I think probably all of this bit that I've just done, you would just do very quickly because you do this sort of thing quite a lot in maths, or you did at GCSE. Another way of approaching exactly the same problem, and just a little bit shorter and possibly a little bit neater, and just to show you can do it in different ways, would be as follows. This time, I've approached it by just saying, okay, what is the drift velocity equal to? So the drift velocity is equal to the current divided by nAqv. But obviously the areas will be different between the two wires. Now, because the current is the same in both wires, the n is the same, effectively it's a constant, and the q is the same, what I can say is that the drift velocity is proportional to 1 over the area. And because they've given us diameters, we can say the drift velocity is proportional to 1 over the diameter squared. Now taking this, I can make two statements. I can say that the drift velocity in A, which has twice the diameter of B, so this time I'm doing it this way around, rather than halving the diameter in B, I'm doubling the diameter in A. The drift velocity in A is 1 over 2d squared, and the drift velocity B is 1 over d squared. Now, if I want to find out what the ratio is between them, I can just divide these two expressions by each other. Oh, sorry, I missed a step. So 2d squared is the same as 4d squared. So I get VA over VB equals d squared over 4d squared. The d squareds cancel and you get a quarter again. Now for some of you, you might think this was a lot simpler. For others, this might make a little more sense. They're exactly the same thing, just approached in a slightly different way. So I suggest that you pick the one that you like and work through it yourself and refer to this video until you feel comfortable with it, and then you can go and approach the exam questions that are on Google Classroom. Thank you and goodbye.